Almost. Okay, so thank you for a kind introduction. Bueno, esto lo quiero decir en español y nada, solo a modo de homenaje mínimo quería dedicar la charla a nuestro querido amigo y compañero Moisés, que hace no tanto estaba por estos pasillos y sentado en estas sillas. Okay, so as you can see, the title of the talk is an enjoyable introduction to the Dirichlet series. So it is true that I will be talking about the Dirichlet series. It is meant to be an introduction, and I will do my best to make it as enjoyable as possible. Okay, so here we have an outline of the talk. I will begin explaining what was the mathematical context in which the Dirichlet series first arose. And then I will move into the introduction of the Dirichlet series. We will begin recalling some basic notions about a more familiar setting of series, which are Taylor series, and we will see what are the corresponding notions in the context of the Dirichlet series. And I will finish presenting two of the most important Banach spaces of the Dirichlet series, H2 and H infinity, which were in fact the first two to be introduced in the mathematical literature. Okay, so it was the end of 18th century. Legendre was trying to prove the quadratic reciprocity theorem, and in his proof, which was incomplete, he claimed the following statement, but he was not able to prove it. And it said that if we have two coprime integers, then the sequence given by A plus k times D contains infinitely many primes. In other words, there are infinitely many primes of this form, okay? But Legendre claimed it, but he was not able to prove it. 3 years later, Gauss gave two proofs of the quadratic reciprocity theorem, which was the theorem that Legendre was trying to prove, but he did not prove the problem, and in fact, he outlined its importance in his Disquisitiones Arithmeticae. So if Gauss thought that this problem was important, it should have some interest. So several mathematicians, among others Legendre, tried to prove the claim. And it was not until 1837 that Dirichlet managed to prove the problem, and he used a rather different approach. And the approach he used was introducing the now known as Dirichletal functions, which was just thinking about the problem in a completely different way. Okay, obviously he did not name this series as Dirichletal functions, and those are not exactly the same functions or the same series as the ones we think of nowadays as the Dirichlet series, but it is a far similar object. Okay, so let me just recall some basic notions about Taylor series, which are well known to all of you. A Taylor series is simply a formal series where we're considering this power series, a sub n times z to the n, where a sub n is just a sequence of complex numbers. Okay, so given us a formal series of this kind, we know the existence of a value R1, which is between 0 and infinity. It can perfectly be 0, for which the series converges in the disk of center 0 and radius R1, and does not converge outside this disk. There exists also a positive real value R2, for which the series converges in the disk of center 0 and radius R2, and does not converge outside this disk. And we can also define a value R3 for which the series converges uniformly in the closed disk. Okay, so in fact these three radii happen to be the same. They all coincide, and also in the radius where the series converges, we know that the function is holomorphic, and we call this radius of convergence. Okay, so let us now see what are the corresponding notions in the setting of Dirichlet series. So, well, first, this is just simple notation that I will be using throughout the talk. Given a real number theta, C theta will be just the half plane consisting on the complex numbers whose real part is greater than theta. And instead of C0, I will use the notation C+. Okay. So a Dirichlet series is a formal series given by this sequence of complex coefficients time n to the minus s, where s is a complex variable. Okay, well, so this is what we formally call a Dirichlet series. The most famous Dirichlet series is Riemann's theta function, which is the Dirichlet series which arises from considering all the coefficients identically equal to 1. And in 1737, Euler computed some values of zeta, in particular zeta of 2, and he was able to prove that equal p to the 2 or times 1/6. And he also proved for S real this following relation, where p are where this product is considered over the prime numbers. Okay, and well, and more than 100 years later, Riemann stated his very well-known Riemann hypothesis, in which he claimed that, or conjectured, that the non-trivial series of theta lie all in the, they all have real part equal to 1/2. Let me just say that in order to this statement to make sense, we need to extend meromorphically because a priori, zeta is defined on the half plane C sub 1, that is for those S whose real part is greater than 1. And in order for this statement to make sense, we have to extend it meromorphically to the right half plane. Okay, so, well, once we have considered this formal series, we associate the following abscissae, which will be playing the role of the radio of convergence in the context of Taylor series. So we have the convergence abscissa, which is defined as the infimum of the real parts of the points for which the series converges. And as it happened for Taylor series, we know that the functions, the Dirichlet series, are holomorphic in the half plane of convergence defined by the abscissa of convergence. So we have convergence to the right of the abscissa. So in the whole half plane defined by the abscissa, and we have that the series does not converge to the left of the abscissa. Similarly, we can define the absolute convergence abscissa and the uniform convergence abscissa, which are defined as the infimum of the real parts of those points for which we have absolute convergence, and in the same fashion for the uniform convergence. Okay, well, we have this relation between the abscissae, that is there where we converge absolutely, we converge uniformly, and where the series converges uniformly, it converges pointwise. But the other need not be true in general. Okay, and we also know that these abscissae are contained in a vertical strip of width 1. So the uniform convergence abscissa and the absolute convergence abscissa cannot exceed the convergence abscissa plus 1. Okay, so this tells us, for instance, once we know that a Dirichlet series converges, we know that not that far it also converges in absolutely and uniformly, which in fact is quite useful when proving some results in this context. And here we have a example of a alternating Dirichlet series. Oops. Yeah. For which we have pointwise convergence in the right half plane and absolute and uniform convergence in the half plane real of S greater than 1. Okay, so well, this relation between the abscissae are not quite difficult. The first, let's say, non-trivial result, well, just here we have a sum up of what are the corresponding notions of Taylor series in the context of the Dirichlet series. So the radio of convergence now are abscissae of convergence. The radio of convergence gave rise to convergence in disks. So in this context, as we have abscissae, we have convergence in half planes. And the fact of the series being holomorphic in the disk, now we have it in a whole half plane. Okay. So I was saying that this relation between the abscissa is not difficult to prove. And the first non-trivial result in this context is related to another abscissa that we can define, which is the boundedness abscissa, and is defined as the infimum of the sigma for which the series is bounded in the corresponding half plane C sigma. So the first non-trivial result proved by Harald Bohr in 1913 states that the uniform convergence abscissa and the boundedness abscissa coincide, are actually the same. Okay, and just as a historical remark regarding Harald Bohr life, we all know that he was a great mathematician, and he also was a silver Olympic medalist with Denmark's football team in 1908. If I'm not wrong, he won with Denmark's national team silver medal. They lost with England 0-2 in the final. Okay, so well, and just I will be denoting by D, by D, the space of all covariant Dirichlet series. Okay, so those series of this form which converge in a certain half plane C theta. Okay, and in the case this series has finitely many terms, as it happens for Taylor series, we will be calling this a Dirichlet polynomial. So this is this is another result regarding Dirichlet series, which is quite deep, and it is another interesting question regarding how separated can the absolute convergence abscissa and the uniform convergence abscissa be. Okay, so Bohr, in fact, it was a question which was raised by Bohr, and Bohr managed to prove that this supremum should be less or equal to 1/2. But he was not able to do better than that. And it was in 1931 when Bonenblust and Hille established the result, and they were able to prove not only that this supremum equals 1/2, but that for each sigma between 0 and 1/2, we can find a Dirichlet series for which the difference between these convergence abscissa, the absolute and the uniform convergence abscissa, is exactly sigma. Okay. So that's all I want to tell regarding the Dirichlet series, and now I'm going to recall some basic notions regarding Banach spaces and Banach spaces of analytic functions, which is the ambient setting in which we work in the thesis. So we know this definition from the bachelor, which is a Banach space is a complete norm space. Okay, and me and we as research team are particularly interested in Banach spaces of analytic functions. Okay, and one of the most classical ones are the Hardy spaces on the unit disk, and I'm going to give very briefly their definition and how somehow the spaces I'm going to introduce can be seen as somehow the version of these spaces in the context of the Dirichlet series. I say somehow because there are many things which occur in the context of on the unit disk that do not happen for our Hardy spaces of Dirichlet series. So the Hardy space H2 of the unit disk consists on those holomorphic functions defined on the unit disk onto C into C, for which we have that the coefficients of the Taylor series are literally to summable. Okay, pretty simple definition. We also have, with the definition, we obtain a Hilbert space structure, and in fact, we can define in a different way. We can define in a equivalent way these spaces via these integral means. Okay, the good thing about defining in this way the classical Hardy space H2 is that it allows us to consider a family for the range P between 1 and infinity, a family of Banach spaces of analytic functions, by considering the following family of norms, which are in fact norms, taking in those supremum over the integral means the value p in the exponent instead of 2. Okay, so this is the interest about the definition through these integral means. Okay, so the spaces we are interested in, which are Banach spaces of Dirichlet series, are in particular Banach spaces of analytic functions, because recall that there, where the Dirichlet series converges, it defines an analytic function. Okay, so when dealing with Banach spaces of Dirichlet series, we will be in the context of Banach spaces of analytic functions. Okay, so let me just tell how these spaces first appear, and it is quite interesting, but because they were introduced for solving the following question, more from which is like it is a question from harmonic analysis or functional analysis, and it was raised. I don't know. I think it was Berlin who first raised it, and he asked the following: if we consider an odd and two periodic function, like a square root sine of pi of x, when will this system of functions be a Riesz basis in L2 of 0, 1? And it was in fact him who in a quite vague way exposed an intuition saying that this could maybe the way of tackling this problem is by considering Dirichlet series. So in 1997, 25 years ago, Hendelman, Lucas, and Saib managed to solve this problem, and to do it, they introduced, they did it introducing this the Hardy space of the Dirichlet series H2, and it meant the origin of the study of these spaces. It is shocking, or at least it is to me, that for solving this question, it was done through by considering these spaces. Okay, so what is H2? Well, H2 is the Banach space consisting of those Dirichlet series, which of this form, for which we have that the coefficients are little L2 summable. Okay, so some comments regarding this definition. First is that we obtain a Banach space of analytic functions in C1/2 because we have that the series converge. The convergence abscissa is less or equal than 1/2, and this is very easy to see using just Cauchy-Schwarz inequality. So we have convergence at least in C1/2, and as there where the Dirichlet series converge, it defines an analytic function. We obtain a Banach space in this half plane. And as it happened for the classical Hardy space of the unit disk, we also obtain a Hilbert space structure by considering the inner product, the little L2 inner product given by the little L2 product of the coefficients of two Dirichlet series, phi and bar phi. Okay, and a third remark, as it happened also for the classical setting of Hardy spaces, we can also define it is far more sophisticated than in the context of classical Hardy spaces. We can also define the spaces considering some integral means which allow us to extend the definition as we did for the classical Hardy spaces for the range P between 1 and infinity. H infinity, I'm going to define it straight away. And basically, it is based on an idea also due to Bohr of seeing the Dirichlet series as functions depending on infinitely many variables in the infinite polydisk. But as I said, constructing these spaces is quite involved. Okay, so the second space, which was also introduced by the authors which introduced H2, is the space H infinity. Okay, and the space H infinity consists on those analytic functions, H infinity of the right half plane, that is those analytic functions which are analytic functions in the right half plane, which happens to be bounded there, and which also can be written as a Dirichlet series. Okay, so those bounded analytic functions on the right half plane of this algebra, which can be also written as Dirichlet series. We can endow the space H infinity with the following norm, which is considered the supremum of the modulus of the function in the right half plane. And we obtain a Banach space structure with this norm, and we obtain that the functions in H infinity have their Van abscissa must be less or equal than 0. And as I mentioned, as I said in the previous slide, the definition for the rest is quite involved. And well, I think I'm almost out of time. So that's all I wanted to. I have here some things like a bonus track, but I think I've already spoken enough. So thank you for your attention.
First, well, thanks, Carlos, to your talk. Really interesting and clear in a really complicated topic. So there are some questions online. No, I think. Okay. And in the IMUS, someone want to ask something about Carlos' talk?
I know that Taylor functions, Taylor series can be used in approximations of derivatives.
Application of Dirichlet series. Well, the interesting thing about which is our main or the center of interest of our research is that, or at least when the context in which Dirichlet series appeared during my bachelor was in analytic number theory related questions, and solving this. So where these Banach spaces H2 and H infinity were introduced for solving this like harmonic analysis problem, they were introduced for in order to solve this this problem. Well, I'm thinking that maybe I should have repeated the question for the people online. Like Seni asked me if yes, in what context one could apply the theory of the Dirichlet series as it happens for Taylor series. And well, as I was saying, the introduction of these spaces was focused on solving this problem. And then people from function analysis and complex analysis theory started to study the properties of these spaces and becoming interested in themselves, so as Banach spaces of analytic functions, which is a little bit the approach as analysts or function analysts and complex analysts. And so these spaces are from 1997. The first important result regarding this space is maybe from 1999, in which the composition operators, the bounding composition operators, which was in fact I think the bonus track I had, was characterized. And then I think 5 years later, in 2002, the definition for the rest range of P was given. And since then, we have studied these spaces. So it's not like, at least I don't. Maybe they are used in another context, but for us, the interests are the Banach spaces themselves, and not how this could be. I don't know. Maybe there are other areas in which, or other problems for which they are quite useful. But as far as I know, yeah, 25 years old. Yeah, all well, more or less my age. So yeah. Yes.
So I was curious if you vision of why the Dirichlet series can be expressed in this mean integral form.
So, like, okay. So, what would be the corresponding definition?
Or this vision of why.
Okay. So the idea is that. Yes, well, the idea is that, and this was an observation done by Bohr, is that, yes. So if you have n to the minus s, okay, n can be written as, by the fundamental theorem of arithmetic, we can write its prime number decomposition. So we can see this as P1 to the alpha 1 to the minus s times PR to the alpha r minus s. And this can be seen as P1 to the minus s, alpha 1, I'm doing nothing here, minus s, alpha to the r. Okay, so if we call zeta 1, P1 to the minus s, this belongs to the unit disk, and so do all the zeta r variables. Okay, so the idea, what we do is we see this series as a alpha zeta. So this can be written as zeta 1, alpha 1, zeta r, alpha r, and we. In order to synthesize this multi-index notation, we write z to the alpha. That would be alpha in negrita. Okay, so okay, and we take here the sum of all the possible multi-indices. So with this change, what we have is a function depending on infinitely many variables. In fact, defined on the infinite. The finite disk, and this process is called. So we are lifting the function, making it dependent on one variable to seen as a function of infinitely many variables, well, once we do this, we define a norm for the Dirichlet polynomials, and we define the HB spaces of the closure in this norm of this polynomial. And the space we obtain is functions which are the limit of in the half plane C1 of Dirichlet polynomials, and which also are the limit in the norm HP of these polynomials. And we can improve this, moving into 1/2. And this is how we obtain the Banach space. This was done by Helson, that the HP spaces are in fact, instead of being defined here, are defined here. And this is how we obtain so we have the H2, I said it was a Banach space of analytic functions in this half plane. So with this theorem due to Helson, we can see these spaces as also defined in the same half plane. So this is like the intuition of. In fact, the first things the authors do when defining H2 in this way is considering this, which is known as the Bohr lift, this operation of seeing this Dirichlet series instead of a function depending on one variable as a function depending on infinitely many. So this is the more or less the intuition. And well, if you are interested, I can tell you where to read.
After in Spanish, maybe complicated.
Now I don't know if I have repeated this question for the online people. No, fantastic.
Are there more questions? Okay, in order to finish the round of questions and your fantastic talk, just talk us about your planning of the following 2 years of thesis, or maybe more, I don't know, and the maybe after the defend your thesis, and also to ask about your experience of the PhD here in the IMUS, here in Seville, out of your home city, Madrid.
Okay. So, well, regarding the first question, the plan is to finish the thesis in a finite amount of time, and
It's more about the topic
well, okay. As you know, well, in January I'm going to Lille for a research stay of 4 months, and I guess after that I should begin thinking about writing the thesis or no, or I don't know, and we'll see what happens after finishing the thesis. I don't know. And well, I'm more or less in the Ecuador. I don't know how to say this in English. In the Ecuador of the thesis. So so far, well, I tend to repeat myself quite a lot. So as I always say, I'm quite happy with the both sides of the thesis, like the mathematical one and the human one. Being I'm not in my home city, so I had to like start from not from zero, but making new friends, etc. So in that sense, I'm quite happy with the good friends and the good people I've met here in the human. That would be in the human side. And regarding the mathematical one, I could not have asked for more. I'm really happy with the topic and with Manolo and Luis, which are great mathematicians and human beings as well. And yeah, that's not the sonroje. And well, yeah, that's basically yeah.
Okay, thank you.
So
Let's
thank you.
thanks.